Time to do some application problems with these logarithmic, exponential, natural base e. Come on, let's do this. First thing I want you to do is on your sheet there, you could cross off numbers 8 and 11. Now we're going to go over some of them right here, and then the assignment is to finish the rest on your own. So we'll kind of do a little bit of each problem. We're going to talk about half-life a lot with these exponential decay problems, and they'll talk about a population doubling, which would be exponential growth. There it is. I was wondering how I'd get to the next slide. So number one, caffeine has a half-life of approximately 5 hours. Suppose you drink a cup of coffee that contains 200 milligrams of caffeine. How long will it take until there is less than 10 milligrams of caffeine left in your bloodstream? Give your answer to 1 decimal place. So here is the exponential decay formula over here. So you'll see that A here is the final quantity. So they're saying our final quantity is 10 milligrams. Well, they're saying less than 10 milligrams, but then we have this A sub 0. That's our initial amount. Now, our initial amount of caffeine was 200 milligrams. Then we have 0.5 because it's talking about half-life. So that would be like 50%. And the exponent is t over h, so time over half-life. So we don't know the time yet. That's what we're trying to figure out. But the half-life is 5 hours. So we're going to have to do some of our logarithmic and exponential equation tricks to work this down. So first thing, I'm going to get rid of that 200 because that has nothing to do with the exponent. So to get rid of that, we'll divide it out. 10 divided by 200 is 0.05, I believe. I'll double check that just because, I make mistakes from time to time. 10 over 200. Cool, 0.05. All right, now, 0.5 to the whatever power gives you 0.05. I don't know. So what we can do is we can log it back. So we can log 0.05 as long as you're doing the same thing to the other side. Log of 0.5 to the t over 5 power. Now this is the part where we're going to kick that t over 5 to the front, which would make it t over 5 times log of 0.5. That's going to equal log of 0.05. So how are we going to get rid of this times log of 0.5? We're going to divide it. Now you can totally knock this out in your calculator right now, and that's all good. Otherwise, the exact answer, you could leave that for now. I'm just going to put it in my calculator here. Log of 0.05 divided by log of 0.5. So I'm getting 4.322. 4.322. That's equal to t over 5. Now, we don't want that 5 there. So, how do you cancel out divided by 5? You multiply by 5. So 4.322 times 5 would give us 21.609. And it said to round to the nearest decimal spot, right? So 21.6. And what are we talking about here with the time in this problem? It was hours. So we'd say 21.6 hours. It's not too bad, right? I mean, your calculator does the heavy lifting. You just have to remember that exponential and logarithmic equations, log it, bring that exponent to the front, and solve what's left. Number 3, a colony of bacteria doubles in size every 20 minutes. Whoa! How long will it take for a colony of 20 to grow to a population of 10,000? So this is a very similar formula, except basically they traded out the 0.5, which was a half-life, for a 2 because it's doubling each time. So the final quantity we want here is 10,000. The initial amount was 20 bacteria. And then we have 2 to the t over d power. The doubling time here is 20 minutes, so t over 20. Again, we'll divide by this number that doesn't have the exponent. So we'll divide by 20. Let's see, 1,000 divided by 2 is 500. I'm always scared that I'm going to just make a silly mistake in these videos. So I'm double checking 10,000 divided by 20. It is 500. Okay. Now, I don't know 2 to the what power gives me 500 because it's not one of those even ones. So we're going to have to log them. Log 500 equals log 2 to the t over 20 power. And then we can take that t to the t over 20, kick it to the front. I'm just going to rewrite the left side here. Equals t over 20 times log 2. What are you going to do to get rid of the log 2? Divide. So log 500 over log 2. I'll go ahead and just do that in my calc. Log of 500 divided by log of 2 is 8.966. 8.966 equals t over 20. Okay, all right. Now we gotta get rid of that 20 by multiplying it. Times 20 equals 179.3. 179.3. Let's see what we're talking about here. We're talking about minutes, so we could say 179.3 minutes, which is basically 3 hours, right? 3 hours would be 180 minutes. So this is pretty darn close to 3 hours. Wow, that's pretty quick. A bacteria culture starts with 6,500 bacteria. After 2.5 hours, there are 208,000 bacteria present. What is the length of the doubling period? Okay, the final amount here was 208,000. The initial amount was 6,500. It's a doubling problem, so there will be a 2 there. Now we have the time over the doubling time. So it says 2.5 hours, so that's our time. We don't know the doubling time. This is interesting. Okay, so again, we're going to have to divide out that 6,500. We're just solving the same type of equation for a different part of the equation. So 208,000 divided by 6,500 is 32. 32 equals 2 to the 2.5 over d. Now there's a few ways we can do this. 2 with an exponent can give you 32. 32 is 2 to the 5th power. So sure, you could log both sides, but if it works out evenly like that, it'll probably just be easier to solve it where we're just solving the exponents. So 2 to the 5th equals 2 to the 2.5 over d. So now if we're solving the exponents, we'll have the equation 5 equals 2.5 over the doubling times d. So we can move stuff around. We can multiply by d on both sides to cancel out the divided by d. 5d equals 2.5. And then we'll just divide by 5. And 2.5 goes into 5 2 times, so it would be 1/2. So we were talking about hours. So the doubling time is a half hour. Or you can say 30 minutes. That would also work. All right, let's see what else we got. How many more do we have here? Oh, continuously compounded problems. So we had a different formula for this back in the day where we could figure this out, but this one works out very nicely. P times E to the RT power. So E is that constant, remember that 2.71, blah, 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 blah. I don't know the decimal. You deposit $975 in an account that pays 5.5% annual interest compounded continuously. What is the balance after 6 years? So the principal, the initial amount we put in was $975. We have our constant E. And then the rate times time. Now the rate is 5.5%. We need it in decimal form. So you can either hit divided by 100 or move the decimal twice. So that would be 0.055 times the time, which is 6 years. So if we clean up that exponent, which you don't need to, your calculator would probably just do that for you, but 0.055 times 6 is 0.33. Now you just got to make sure that you do exponents first and then multiply by the 975. And many calculators will do the order of operations for you, so just check. But I know mine does. So 975 times, remember to find that E button, E to the 0.33 power. Wow, nice. Good investment. $1,356.19. Way to go. Look at us making some money. Number 13, there are 40,000 homes in your city. Each year, 10% of the homes are expected to disconnect from the septic systems and connect to the sewer system. Write an exponential decay model for the number of homes that still use septic systems. Use the model to estimate the number of homes using septic systems after 5 years. So our initial amount is the 40,000 homes. Now, 10% are dropping off here. So if you did 100% minus the 10% decay, that gives you 90% of the people each year. So in decimal form, that would be 0.9, right? Because that's the 1 minus 0.1, or 100% minus 10%. Because 10% are disconnecting every year. The exponent is t in time, so we want to know when it's going to be 5 years. Oh, first I just had to write the model. Oh, okay. So to the t power initially, we'll say equals a of t. There's our function. Now we have to evaluate that function for 5. So a of 5 equals 40,000 times 0.9 to the 5th power. And again, most calculators will correctly put this in order of operations. 40,000 times 0.9 to the 5th. 23,619.6. So let's call it 23,620 homes. They're still using that septic system. Now, if it said how many are not using the septic system anymore, you could just do 40,000 minus that 23,620. I'm just going to check how many we have left here. 14, 21. All right, 14 and 21. We're almost there. A new car costs $23,000. The value decreases by 15% each year. Think of the decay. Starting at 100%, it's dropping 15%. 100 minus 15 is 85%. So it's retaining 85% of its value each year. Write an exponential decay model for the car's value. Use the model to estimate the value after 3 years. So let's say a of t again, just for function notation. The initial amount is 23 large. It's retaining 85% of its value. Again, 100% minus the 15%. So in decimal form, that's 0.85 to the t power. Now we have to evaluate it for 3 years. We have to drop our marker. A of 3 equals 23,000. That's 0.85 to the 3rd. You know the song. I hope you were singing along at home. Doesn't look like the decimals there. Wow, it's just getting worse. 23,000 times 0.85 to the 3rd, $14,000. $14,124.88. Mine said 0.875, but you're not going to say 87.5 cents, right? Come on, that's just silly. What is the future amount of $12,000 invested for 5 years at 14% compounded monthly? So the other one, it was just compounded continuously, so we were able to use that PE to the RT power. But here it's compounded monthly. So again, the principal is the amount we're putting in. We have 1 plus, the rate is 14%. Now we always have to do it in decimal form. So that would be 0.14. It's divided by n, and you remember n is the number of times it's compounded per year, and it says monthly. So that would be 12 times a year. That same number comes up here 12 times, and you multiply by the number of years, which is 5 years. Because this exponent is saying, well, how many times was it calculated? It's done every month, and there's 5 years, so 12 times 5 would give us 60. So if we just clean up some stuff here, I'm going to clean up the inside of the parentheses. And order of operations would say you do that fraction first. So 0.14 divided by 12, then I'll add the 1. You get 1.011, and then the 6 repeats. But I know 12 times 5 is 60, so I'm just going to take that right now in my calculator, take it to the 60th power, and get 2.00560,979, all that stuff. And then I'll just multiply that by 12,000. Woo, wait! Way to go! This was 5 years, $24,067.32. That's awesome. Good for you. Now, if they said, well, how much did they make in interest then? Here's their final amount. How much did they put in initially? They put in 12 grand. So if you just subtracted the 12,000 that we put in, they made over $12,000 just in compound interest. That's awesome. So there we go. We got some for you to try out. You got this.